In the beginning, there was nothing. No space, no time, no matter. But then, something unimaginable happened. A singularity appeared, a point in space and time where the laws of physics as we know them broke down. This singularity contained all the energy, all the matter, and all the information that would ever exist in the universe. And then, it exploded. The Big Bang. The singularity expanded rapidly, faster than the speed of light. As it expanded, it cooled, and the energy within it transformed into subatomic particles, protons, neutrons, and electrons. These particles collided and combined to form the first atoms, hydrogen and helium. As the universe continued to expand and cool, gravity pulled these atoms together to form the first stars and galaxies. And as these stars burned and died, they scattered the heavier elements that make up everything we know today, the Earth, the planets, and even us. We are all made of stardust, remnants of the very first moments of the universe. The Big Bang. The beginning of everything. The cosmic inflation. The Big Bang. This tremendous explosion marked the birth of our universe, some 13.8 billion years ago. But scientists have long wondered about the moments immediately following the Big Bang. One theory that has gained significant attention is the concept of Big Bang inflation. According to this theory, the universe underwent a period of exponential expansion just after the Big Bang. This rapid expansion is thought to have occurred when the universe was just a fraction of a second old. But why is this important? Well, the Big Bang inflation is believed to have smoothed out and homogenized the universe on a large scale. Without this period of rapid expansion, it is likely that the universe would be much more uneven and chaotic. The theory of Big Bang inflation was developed in the 1980s as a way to address some of the problems with the standard Big Bang model, such as the horizon problem and the flatness problem. And today, it is widely accepted as an important part of the standard cosmological model. So next time you look up at the night sky and marvel at the vastness and beauty of the universe, remember that it may have all started with a tiny spark of energy, the Big Bang, and a brief moment of inflation. The universe we see today is vast and vast, with billions of galaxies spread out across the cosmos. But how did it get this way? The answer, according to the theory of cosmic inflation, lies in a brief period of rapid expansion that occurred just a fraction of a second after the Big Bang. This period of cosmic inflation is thought to have stretched the universe to a much larger size than it would have been otherwise, smoothing out any irregularities that may have existed in the early universe. But what caused this period of cosmic inflation? That is a question that scientists are still trying to answer. One possibility is that cosmic inflation was caused by a field of energy, otherwise known as dark matter and dark energy. that permeated the universe during the very early stages of its expansion. This field of energy is thought to have had negative pressure, which would have caused the universe to expand faster than it would have under the influence of normal matter and energy alone. Other theories have also been proposed to explain cosmic inflation, but at this point, there is not yet a widely accepted explanation for this phenomenon. Despite this, the theory of cosmic inflation remains an important part of our understanding of the early universe, and it continues to be a subject of active research and debate among scientists and cosmologists. Nucleosynthesis is the process by which new atomic nuclei are created. There are several ways that nucleosynthesis can occur, but the most well-known is through the fusion of lighter elements to form heavier ones. This process releases a tremendous amount of energy, and is the primary source of energy for stars, including our Sun. But how did the universe's first elements form? The first elements were formed in the aftermath of the Big Bang, about 13.8 billion years ago. In the extremely high temperatures and densities present at that time, matter as we know it today did not exist. Instead, the universe was filled with a hot, dense soup of quarks, gluons, and other elementary particles. Within the first few minutes of the universe's existence, these subatomic particles began to combine through the strong nuclear force, forming the first atomic nuclei. This process is known as Big Bang nucleosynthesis. As the universe cooled and expanded, these particles began to combine and form more stable, composite particles such as protons and neutrons. These, in turn, combined to form the first atoms, which were mostly hydrogen and helium. During Big Bang nucleosynthesis, the lightest elements, such as hydrogen, helium, and lithium, were formed. These elements would eventually go on to form the first stars and galaxies, and serve as the building blocks for all the heavier elements we see today. Over time, as the universe cooled and expanded further, more and more elements were formed through a variety of processes, including nuclear fusion in stars and supernovae, and through the capture of free neutrons by heavier elements. Nucleosynthesis is an ongoing process that continues to shape the universe we know today. From the formation of the first elements to the fusion that occurs within the cores of stars, nucleosynthesis plays a vital role in the evolution and diversity of the universe. Today, there are over 100 known elements, and they make up everything in the universe, from the stars and planets, to the air we breathe, and the food we eat. Deep in the heart of our galaxy, there lies an object so mysterious and powerful, that it defies our understanding of the universe. This is a black hole. A black hole is a region in space where the gravitational pull is so strong, that nothing, not even light, can escape it. They are formed when a massive star dies, and its core collapses under the force of its own gravity. Black holes are invisible, as their immense gravity prevents light from escaping. However, their presence can be detected by observing the effects of their gravity on nearby matter. For example, a black hole can pull in gas and dust from its surroundings, forming a bright accretion disk around it. Black holes are also known to have a profound effect on the space-time around them, warping it and causing it to bend. This can cause nearby objects to move in strange and unexpected ways. The Big Bang theory is the prevailing cosmological model that explains the origins of the universe. According to this theory, the universe began as an incredibly dense and hot state, and has been expanding and cooling ever since. The evidence for the Big Bang includes the cosmic microwave background radiation, the large-scale structure of the universe, and the abundance of light elements. There is a probability that the Big Bang might have started from a burst of a black hole. This idea is known as the Big Bang from a black hole, or black hole Big Bang theory. Our universe might have begun as a singularity, a point of infinite density and temperature, that existed within a pre-existing universe, and that the singularity expanded and cooled to form our observable universe. The pre-existing universe would have been the result of a previous Big Bang, which itself would have formed from a black hole in the previous universe, and so on. If this theory is correct, then all the black holes in the universe will collapse one day, to form a singularity. Black holes are still largely a mystery to us, and scientists continue to study them in order to understand more about the universe and our place in it. We see a panoramic view of the vast and beautiful universe. Stars. Galaxies. And nebulae of different shapes and colors fill the screen. The universe is a vast and complex entity, filled with wonders that we are only beginning to understand. But, have you ever wondered, what keeps this beautiful, vast, and seemingly chaotic place stable? The stability of the universe is maintained by a balance of forces and the properties of matter and energy within it. The four fundamental forces: gravitational, electromagnetic, weak nuclear, and strong nuclear work together to keep matter and energy in a state of equilibrium. Additionally, the distribution of matter and energy throughout the universe is such that it does not collapse under the force of gravity, and the expansion of the universe is also slowing down, which helps to maintain a stable state. Matter and energy are in a state of equilibrium because of the balance of forces and the laws of physics that govern their behavior. For example, the gravitational force attracts matter and energy towards each other, while the electromagnetic force can repel them. The balance between these forces helps to keep the universe in a state of equilibrium. Additionally, the laws of physics, such as the conservation of energy and momentum, help to maintain equilibrium by ensuring that the total amount of matter and energy in the universe remains constant. In terms of thermodynamics, the second law of thermodynamics states that entropy, a measure of disorder in a system, always increases over time. This means that systems tend to move towards equilibrium, where the entropy is at a maximum. This is why systems in nature tend to move towards a state of equilibrium, where the energy is evenly distributed and there is no more useful energy available to be converted into work. In summary, the balance of forces and the laws of physics help to maintain equilibrium in the universe, which is essential for its stability and continuity. Thanks for watching. Like and subscribe for more videos.